you. In the last class, we were talking about mechanical properties of solids, and in that, we talked about stress. So, what exactly is stress? Stress is force acting per unit area on solid. Force acting per unit area on solid is called stress. After that, we talked that on the basis of the way force is exerted on the object, stress can be of three types. First is longitudinal stress, second is shear stress, and third is volumetric stress. So after that we talked about longitudinal stress, that it is of two types. One is tensile and other one is compressive. Okay. And then we talked, performed some question also based on that. Now we are going to talk further. So next is shear stress. Shear stress. So what is shear stress? Let us see. So it is a stress. It is the stress which is developed in an object, which is developed in an object when force is exerted on it, when force is exerted on it parallel to the surface, parallel to the surface. Okay. So what is the criteria how the force is to be exerted in this case? Force has to be exerted parallel to the surface. Somebody's mic is unmuted. Please mute it. Somebody's mic is unmuted. Please mute it. Please keep your mic mute. Shivam. Shivam. Okay. So what I was telling you, that shear stress is the stress which is developed in an object when force is exerted on it parallel to the surface. Now try to understand what do you mean by force exerted parallel to the surface. Suppose there is some rusting occurred on an iron object. So if you want to remove that rust, what you need to do? You need to rub it. You need to rub it via sandpaper, right? So when you are rubbing it, how you are exerting force on it? You are exerting force parallel to it. Okay. So that kind of force is going to produce shear stress. Secondly, suppose you need to do ironing on clothes. So when you do ironing, how you are exerting force on the cloth? That force is exerted parallel to the cloth, right? So that you can remove those. Uh, Hello, can you hear me? So that kind of force is called, or that kind of stress is called basically shear stress. Third example is, suppose if you install an AC in wall. So when you have installed that AC in wall, now that wall is not allowing AC to fall, correct? Wall is not allowing the AC to fall. So wall is exerting force on AC along the wall opposite to the gravity. So that kind of force will also produce shear stress in wall. All right. If you become Spider-Man, suppose, and if you start crawling on wall or walls, crawling I am saying, then the force exerted by wall on you or by you on wall will produce shear stress on wall. All right. So these were a few examples in which the force is being exerted parallel to the object. Just to give you example, this is suppose an object, and if forces are exerted, one force in this direction, one force in this direction, so you can see that forces are parallel. Forces are parallel. Okay. Now due to these forces, object will get deformed also. Object will get deformed also. So how it will be deformed? Let us see. It will be deformed in such a way, like this. Okay. So deformation will be caused because forces are acting on it. Okay. So I am writing the definition now. So shear stress is equal to F parallel upon area. Okay. Shear stress is equal to F parallel upon area. All right. Area is the area on which the force is acting, not the entire area. Okay. So let me give you a question. An AC of mass 20 kg. I'm taking a tentative figure. Value can be something else also. An AC of mass 20 kg and length 1 meter, width half, or you can say 1 by 3 meter, and height 1 by 4 meter is mounted on a wall. Obviously wall will be vertical. Okay. Find shear stress produced by it. Find shear stress produced by it. Please find everyone. When we are saying height in this, height means the length which is coming out of the wall. That is height. Okay. For an AC, height means the part which is coming out of the wall. That length is height. Please give me the answer. Yesterday I got to know one interesting fact. There are some students who have written exam in Mount Letera, and now they are asking, sir, from when our classes will start? They didn't ask me directly. They asked to our staff. So I told the staff that tell them that we are printing invitation cards. Once the cards will be printed, then we'll dispatch those cards with registered post. And after getting that registered post, if they feel like, they can join classes. After that, I told the staff to tell them that classes are already started. I don't know why such questions they are even asking. I guess they were expecting at least 15 days break after writing such difficult exams, right? And with such bright questions, I don't know how they convince parents also with their questions. Was it you, Hiram? Was that you?
No, sir.
Okay, you were so happy, so I thought, hmm. Okay, everyone, let's not waste time. F will be mg, AC will be somewhat like this. Okay, this is 1 meter, it is given. Then width is how much? 1 by 3. Okay, so mg will be acting downward, and mg will be 20g. So F is equal to 20g is equal to 200 Newton is equal to 200 Newton. All right. Area A is equal to 1 into 1 by 3. So that will be 1 by 3 meter square. So stress, which stress? Shear is equal to F parallel upon A. So F parallel is 200 upon 1 by 3, and that will be 600 Pascal. So answer will be 600 Pascal. Understood, everyone? Any doubt, any question? Any doubt, any question? All right. All right. So this was Amod is saying, sir, won't act MG act at the side of AC? Which side AC? Normally you install your AC horizontally, the way we have installed. So which side of AC you want to apply MG? Amod? Amod.
Or the height and the breadth, sir.
See, height is outside, as I told you in the beginning itself. All right. And breadth I have mentioned 1 by 3. The height 1 by 4 I did not even mention because it is not applicable for area. Understood? Hello? Understood?
Mhm. Yes, sir.
Okay. So now we are moving towards volumetric stress. There is not much thing to be taught in this shear stress. Volumetric. stress. Now try to understand. Suppose this is an object. Okay. So this is an object and you want to exert volumetric stress on it. So what do you need to do? And what is volumetric stress? Let us understand that also. If force is applied on an object from all directions, if force is exerted on an object from all directions, okay, then the stress produced due to that, then the stress produced due to that is called volumetric stress. Okay. So if suppose this is force, these are forces which are acting from all directions, and due to that, if this force will act, obviously its size will shrink. So its size will become lesser or reduced. Okay. So such kind of stress which acts on an object throughout the volume is called volumetric stress. Okay, so please write. If force is applied, if force is applied on an object from all directions, okay, if force is applied on an object from all directions, then the stress produced, then the stress produced in it is called volumetric stress. Volumetric stress. Okay. Now try to understand, everyone. Try to understand. Suppose there is a person, okay, and you got angry on that person, and because of that you slapped that person. Okay. Just it is an example. Don't take it personally. Don't try this at home also. So when you got angry, you slapped that person. All right. Now when you slapped, it was a little bit hard, and due to that, your fingerprints are now marked on the person's face. But the point is, are you able to exert volumetric stress? No. Why? Because the places where you exerted the force, only that much place is deformed, not the entire body. Right? So basically, in your first endeavor, you are not able to create volumetric stress. Okay? Or that means what you can simply say that slapping cannot cause volumetric stress. What it can do is it can create compressive stress. That is a part of longitudinal, right? But volumetric stress is not possible due to that. Now, after realizing your inability to create volumetric stress by slapping, you took a stick and this time you have decided that come what may, I'll make sure that volumetric stress is developed. So you hit the person by a stick. So suppose you hit it in the back. So the only part where the stick is touching the person, that will get deformed, only that part, not the entire body. So here also you are unable to produce volumetric stress because that was a localized thing at some particular point where you have hit. So my question to you is, how to create volumetric stress or how to exert volumetric stress in solids. Okay. My question is very simple. How to exert volumetric stress in solids or on solids? Can you explain, anyone? Can you help me out with this? How to exert volumetric stress? Hmm. Aradhya is saying increase air pressure. Anyone else? Anyone else? Okay. Amod is saying put in water, heat. By heating, how you are going to exert volumetric stress, Rishikesh? By heating, how you are going to produce volumetric stress? Rishi, how you are going to produce volumetric stress by heating? First heat and then exert force, then directly exert force. No, why heating? Sustain explosion in shape similar to the body. Hmm? Make explosion in a shape similar to the body. All right. Okay, everyone, please pay attention. You guys are very close to the correct thing. It is really very difficult to exert volumetric stress on a solid object. One thing what you can do is you can create a cylinder, suppose, and in that cylinder make that object stand if he is a person, or if it is an object, put it simply like that. And after that, what you can do is you can immerse that object in very fine sand like talcum powder. So as it is talcum powder, it is solid, so it is going to exert force, and the talcum powder will be around the whole object, so the force will also be uniformly acting from all directions. So this can be one way. Another is the way Amod said, put that object in water. Why? Because when you are putting the object in water, pressure will act on the object from all directions. Pressure will act on the object from all directions because liquids and gases, they exert pressure on everything that comes in their contact uniformly from all directions. But did you notice which word I used? I used pressure. Okay. So the interesting thing is the volumetric stress, the volumetric stress in liquids and gases is called as pressure. Okay. But if we are talking in terms of solids, Then we use word volumetric stress. Then we use word volumetric stress. So volumetric stress becomes pressure if you are talking in terms of liquids and gases. Okay, remember this fact. Remember this fact. Okay, you must have seen people playing a game called rugby. In rugby, what happens? One person falls and so many other persons start falling on it from all possible directions. That can also be treated as one form of creating volumetric stress. Yes or no? I don't know how they survive after that, but yes, that can be treated as volumetric stress. Okay. So again, volumetric stress is equal to volumetric stress is equal to force upon area. Okay. So V for volumetric is equal to F upon A. F upon A. All right. All right. Now also note that star point which I told you. Volumetric stress in liquids and gases is called pressure or becomes pressure. Volumetric stress in liquids and gases becomes or is called pressure. If you notice, even their units are same, right? So definition is same, units are same. It will only depend where you are talking in on solids or in liquids or in gases, then the things will be different. Otherwise, it will become same. Line will be very blurred if you go into liquids or if you go into gases and then you start talking about volumetric stress. Okay, just to give you example, suppose if you are filling air in a balloon, if you are filling air in a balloon, then what is happening? Inside air pressure is there and the balloon surface is experiencing what? Volumetric stress. Balloon surface will experience volumetric stress. All right, like that. So, how many types of stresses are there? Three types. Number one, longitudinal stress. Number two, shear stress. And number three is volumetric stress. Now, when stress is acting on an object, then what happens? So, whenever stress is applied on an object, the shape of object gets deformed. Shape of objects get deformed. Okay. So, please write. We are moving to next topic actually. Whenever stress is applied on an object, whenever stress is applied on an object, its shape gets deformed. Its shape gets deformed. Okay. So, pay attention. We are actually talking about new term and that is called strain. All right. So, what exactly is strain? Ratio of change in shape to the original shape is called strain. Okay. So what is strain? strain is equal to change in shape upon original shape. Okay. So strain is change in shape upon original shape. All right. So that will be the strain. Okay. Now if you notice, the change in shape and original shape both will have same dimensions. All right. So strain will be a dimensionless quantity. Strain is a dimensionless quantity. Someone has unmuted the mic, and that someone is Anshul. Anshul, put your mic on mute. Anshul is not listening. All right. So strain is a dimensionless quantity. So that means dimensions of stress is equal to dimensions of stress is equal to m naught, L naught, T naught. Dimensions of stress is equal to m naught, L naught, T naught. Okay. Now, how many types of strains are there? So on the basis of type of stress applied, strains are also of three types. Okay. So according to the type of stress applied, strain is also of three type. Okay. So which three type? Obviously, number one, longitudinal strain. Number two, shear strain. And number three, volumetric strain. Okay, volumetric strain. So according to the type of stress applied, strain is also of three types. Number one, longitudinal strain. Number two, shear strain. Number three is volumetric strain. Okay.
So please scroll up.
How much? Is it okay?
Done, sir.
All right. Okay. So number one, longitudinal strain. Okay. So what is longitudinal strain? Pay attention. If stress is applied on an object, if stress is applied on an object along its length, then strain produced strain produced in it is called longitudinal strain. Longitudinal strain. Try to understand what is happening here. Okay. So here, this is length, or you can say this is initial dimension. So you can call it L naught. L naught means initial length. Now, when you have applied the strain, or you can say stress. So when you have applied the stress, then the object will become like this. Okay. So this is F, this is F. Now the length has become L naught plus delta L. So length has been changed by how much? It is changed by, or you can say increased by delta L. Okay. So longitudinal strain will be change in length, upon original length, or you can say initial length. All right, so delta is symbol for this. L for longitudinal is equal to, this is delta L upon L naught. Okay, please note delta L upon L naught.
So what's the difference between stress and strain?
अच्छा, स्ट्रेस इज थप्पड़ खाना, स्ट्रेन इज उसके बाद पेन फील करना. दैट इज द डिफरेंस. हेलो हेलो. Strain is basically caused due to stress. Strain is caused due to stress. Are you getting the point?
Yes, sir.
So that is stress, and that is the difference basically. Try to understand. Suppose if I pull your hand, okay, if I exert force on your hand and I try to pull that, so the force which I am exerting on your hand, that will cause stress in your hand. Okay, due to the force which I exerted, what will happen? Stress will be developed in your hand, correct? And that stress will cause strain. Okay, the exact difference, if you want to understand between stress and strain, it is basically cause and effect. So cause is stress and effect is strain. Are you getting it? Hello, have you understood?
Yes, sir.
Okay, so basically it is cause and effect. When you are exerting any stress on any object, So that object's shape will get deformed. All right. So that deformation is basically caused due to stress. Deformation is caused due to stress, right? Like that. Now, this was the case when the force, or you can say stress, is uh, pull type. If it is push type, let us see that also. So this is an object. All right. Now, if force was acting on it in this direction, so basically it will cause stress. Now, due to that, what will happen? So this was L naught, and this time it is L naught minus delta L. Okay. So this time delta L will be minus delta L upon L naught. Okay. Okay. Any doubt, any question? Any doubt, any question? Good. Next. Let us talk about shear strain.
So please scroll up.
Noted. Noted. Yes, no.
Done, sir.
Okay. So the next one which I was about to tell you is shear strain. So what is shear strain? If shear stress is applied on an object, so or when shear stress, when shear stress is applied on an object, the strain produced is called shear strain. Okay. The strain produced is called shear strain. So try to understand the previous example which I gave. Okay. So this is an object. Now when it is getting deformed, So it will happen like this. So this was initial height and this deformation is x. All right. So you can see that there is an angle which is being developed here. And obviously there is force which is causing the stress. Okay. So shear strain is equal to x upon h. And actually that is theta, because when angle is very small, tan theta is equal to theta. X upon h is nothing but tan theta. X upon h is nothing but tan theta. Okay. Please note. Noted, everyone? So this is your shear strain. This is your shear strain. Okay.
Excuse me, sir.
Yes.
Sir, that is x upon a or h.
H. This is
Okay.
H. Okay. Next comes volumetric strain.
Please scroll up.
Yash is saying, sir, whenever I try to open Teams,
Sir, that.
it always and password every single time. They don't trust you, Yash. You need to develop the trust. Okay. You need to be more sincere so that they can trust you. Okay. As of now, I think they are not treating you as a trustworthy person. Anyone else is facing the same problem? Anyone else is facing the same problem as Yash, Kurav? No, nobody mentioned. Trust issues. Okay. Volumetric strain. All right. So this was your initial volume, V naught, and this is V naught minus delta V. Okay. So when volumetric stress is applied on an object, the strain produced is called volumetric strain. When volumetric stress is applied on an object, when volumetric stress is applied on an object, strain produced is called strain produced is called volumetric strain. strain produced is called volumetric strain. Okay. So delta V, or you can say write in words first. Volumetric strain is equal to change in volume upon original volume. Okay, so delta V is equal to minus delta V upon V naught. Okay. Any doubt, any question so far? Any doubt, any question so far? Anyone? So if you recollect and if you try to summarize, things are very simple. Very.
Sir, how it will be negative delta V?
Because Chotu, final volume is lesser. Final volume is
Okay, sir.
lesser. So final minus initial becomes negative. Okay.
Okay, sir. Okay.
Good.
Got it, sir.
So the point which I am trying to tell you, that things are very simple, everyone. You have longitudinal stress, you have shear stress, and you have volumetric stress. And corresponding to these three stresses, we have three types of volume strains: longitudinal strain, shear strain, and volumetric strain. All right. Okay. So very easy things are. Now let us talk about Hooke's law.
So please scroll up to the diagram. Done, sir.
All right. Hooke's law. So Hooke's law says within the elastic limit, okay, according to this law, within the elastic limit, ratio of, or if you don't want to write in terms of ratio, then what you can write? According to this law, within the elastic limit, strain produced in an object is proportional to the stress applied on it. Okay. So strain is proportional to stress, and that gives us stress upon strain is equal to constant. Okay. But is there any condition? Yes. What is the condition? Within the elastic limit. Within the elastic limit. Okay. Okay. So that is the condition. Stress upon strain is equal to constant. Now, I am just trying to explain this in a vague term. I am not doing it perfectly scientifically, but still you can understand and you can realize that what I am doing. Suppose, just to give you example, one of your friend is holding your hand and he is trying to twist your hand the way friends do mischief. All right. So if he twists it slightly and if he releases that, your hand is fine. Okay. Now, second time he is twisting it a little bit more, so you will feel more pain. But if he release that, your hand will be fine. Okay. So third time he increased the twist, pain will be more, but still it is within the elastic limit. So once he removes that twisting force, your hand becomes fine again. But in fourth time, if he goes beyond the elastic limit and twist your hand more, this time what will happen? Your bone will get dislocated because it has gone beyond the elastic limit. Some serious injury can also happen. Now, if he releases the hand, will your hand be perfectly fine? No. This time you need to go to doctor. So what has happened in fourth time? He has gone beyond the elastic limit, right? So same is happening in Hooke's law. Your stress upon strain is equal to constant. This is valid only till things are remaining within the elastic limit. If you go beyond the elastic limit, then stress and strain will not be proportional. Your stress and strain will not be proportional beyond the elastic limit. Okay. So this is applicable. Hooke's law is applicable only within the elastic limit. Okay. So please mention this specifically. Hooke's law is applicable only within the elastic limit. Only within the elastic limit. Okay. Remember that. Remember that. All right. Based on that, there is a stress strain curve also. So please draw that. So while we are drawing this curve, imagine that there is a wire which is hanging from a ceiling, metal wire. Okay. There is a metal wire which is hanging from a ceiling, and what you are doing, you are exerting force on the metal wire on its free end, and you keep on increasing that force. So when you are increasing that force, stress will also get increased. Stress will also get increased. Yes or no? Yes. So how stress and strain will work, let us see. How the graph will be, let us see. So pay attention. So your graph will be somewhat like this. Okay. Now what are special points in this? Up to this, it is proportional limit. Okay. Now if you see beyond this also, though proportionality is not there, but still elastic limit is there. Elastic limit. Okay, what is elastic limit? We'll talk about it. Then comes plastic region. And then the final point is the fracture point. Fracture point. Okay.
What is this graph about?
This is graph between stress and strain developed. This
Okay.
graph is stress and strain developed. Okay.
Yes, sir.
So on this axis it is stress, and on this axis it is strain. Okay. Now try to understand what is happening up to the first dotted line which I have drawn. Okay. Your stress and strain are proportional. If you increase the stress, proportionally strain will also increase. If you increase the stress further, strain will be further increased. Now when you have reached to the proportional limit, and if you go beyond that, now what will happen? When you are increasing the stress, strain will increase, but not proportionally. Not proportionally. All right. Beyond that, suppose if you have reached beyond up to the elastic limit. Now what is meaning of elastic limit? The elastic limit tells us that if you remove the deforming force, if you remove the deforming stress, then the object will regain its shape back. If you remove the deforming force, then the object will regain its shape back. Okay, up to that point, elastic limit. But if you go beyond the elastic limit, then object will not regain its shape exactly back. Okay, some deformation will be left in the object. Some deformation will be left in the object, and that region is, that's why called plastic region, because deformation is now permanent. Deformation is now permanent. Okay, so even if you cross the elastic limit, even if you remove the deforming force or the stress, then the shape will not be regained by the object perfectly. Shape will not be regained by the object perfectly, and some deformation will be left in it. That's why that region is called plastic region. Okay, and even after that, if you don't stop and if you keep on increasing the stress, then there will be a point at which the wire will break, and that point is called fracture point. That point is called fracture point. Are you getting it, everyone? So proportional limit is the limit till which stress is proportional to strain. Proportional limit is the limit till which stress is proportional to strain. Elastic limit is the limit till which if you remove the stress, the object will regain its shape back. And the plastic region is the region in which if once object goes beyond the elastic limit, then the deformation, some deformation will remain there in the object permanently, and that's why it is called plastic region. And if you keep on increasing the stress, there comes a point beyond which the object will break. Okay, so that point is called fracture point. Any doubt, any question so far? This is important graph, remember that. This is important graph. Many times they ask question based on this graph, though that question is simply based on understanding that how well you understand things, but still it is important to know things. All right, so I suggest all of you to keep this graph in your mind. Okay, don't ignore graphs. Basically, don't ignore graphs. All right, okay, so now let us move further. So there was a scientist called Young, Thomas Young. Okay, so Young's modulus. Young was a very smart person. Young was a very smart person. Why smart? You will realize very soon. Now, as per Hooke, if you pay attention, everyone, as per Hooke's law, stress upon strain is equal to constant. Yes or no? As per Hooke, stress upon strain is equal to constant. Now young bhaiya came and said, wait. He said within the elastic limit. Within the elastic limit, ratio of longitudinal stress and longitudinal strain will remain constant, and that will be called Young's modulus. And that will be called Young's modulus. So basically, he gave a very dignified name to that term constant, and he said this concept will be called Young's modulus. All right. So the provision was already there by Hooke. By Hooke, provision was there. Mr. Young utilized that and said, okay, read this, study this now onwards. So please write in words. According to Young, according to Young, within the elastic limit, within the elastic limit, ratio of longitudinal stress and longitudinal strain remain constant for the object and is called Young's modulus. Young's modulus for the object, right? So that's a smart work. That's a really smart work. Why? Stress upon strain was anyway constant. You added longitudinal in both, longitudinal stress upon longitudinal strain, and then you named that constant as Young's modulus. Correct? That was brilliant. Now pay attention. Suppose there is a wire, and through that wire a block of mass m is hanging. Okay. So now y is Young's modulus, and that will be F upon A, because that is stress, and strain will be delta L upon L. So y is equal to F upon A upon delta L by L. So that becomes y is equal to FL upon A delta L. So this is your Young's modulus for this case. Now, was that this easy as it is visible here? No, actually. What he did, he performed experiments for many objects, and he defined Young's modulus for all those objects, and that study is even now there. So basically, he defined Young's modulus as one of the most important property of objects. Okay, so that's why his work is important. That's why his work is important. Okay, let me give you some questions. So let me use this diagram directly. Question. This is L, this is A, this is Y. L is length of the wire, A is area of cross section of the wire, and Y is Young's modulus. M is the mass of block. For the given system, find increase in length of wire. Find increase in length of wire. Please find.
Can you please scroll up a bit? Done.
Okay. So let me solve this because it is not difficult question. Mg is acting downward, tension is acting upward, so T minus Mg is equal to 0. So T comes out to be Mg. Okay. Now by Young's modulus, so Y is equal to F upon A upon delta L by L. So Y is Y, F is Mg upon A upon delta L by L, right? So that will give us delta L is equal to MGL upon AY. Please see whether you are getting the same answer or not. Okay. Done, everyone? Noted? Noted?
Yes, sir.
Okay, good. Good. Next question. So basically this is a rope. Okay. M is total mass, L is length, A is area of cross section, and Y is Young's modulus. Okay, you can call it uniform rope. Now while this rope is hanging, due to its own weight, its length will increase. So the question says find increase in length of rope due to its own weight. Okay, please find everyone. And it's a good question. It's a good question. Someone's mic is unmuted. No, Sakshi, answer will not be MGL upon AY. Otherwise, what will be the difference between this question and that question? Okay, everyone, please pay attention and listen very carefully what I am doing. Listen very carefully what I am doing. What I am doing in this question is I am going at a distance x from the bottom, that means free end, and then I am considering an element of length dx. Okay. Now, आराध्य ऐसे हवा में बातें मत करो. Give me the number. Give me the number. I am going at distance, taking element, मतलब integration. ऐसे थोड़ी होगा. Give me the answer. Pay attention. Now tension at this point, P. Suppose this point is P, so tension will be TP. That will be only due to the part which is hanging below. So TP minus mg is equal to 0. And TP will be mg, and that small m will be nothing but, pay attention everyone, m by L. This is mass per unit length into x. This is length, so this becomes mass into g. This is equation number 1. Okay. Okay. Uh. Okay. Just one thing I am doing. I am making this x as y. This going at a distance x and taking an element, I am making it as y. So this element has length dy. Okay. Only that change I have made. Rather than taking x as variable, I have taken y as variable. Okay. That is not going to make any difference. But I took it for a reason that you will realize in a short while. So this is TP. Okay. Now pay attention. If delta L, okay, or D of delta L, you can say, if D of delta L is increase in length of, if D of delta L is increase in length of dy, then by Young's modulus. Then by Young's modulus. So pay attention everyone. Capital Y is equal to F upon A upon delta L upon L. This is the formula. So capital Y is Y. F is how much? Small mg. So that will be mg upon Ly. Mg upon Ly upon A upon delta L. So delta L is D of delta L upon L. L is dy here. Okay. So just to avoid all such small confusions, I did it like this. Be very clear, capital Y is a different variable, small y is a different variable. Okay. Be very clear about this. So from here, what
have
we
you
can
written
say?
in the denominator? The D of what
D
is
of
that?
delta L. I have mentioned it here.
Okay, sir.
I have mentioned it here.
Yes, sir.
Okay.
Understood.
Yeah. So now this will give you y is equal to capital M G y upon AL. Okay. This dy goes here and d delta L is here. Okay. So in next step, what we can do, we can take d delta L here is equal to capital M G small y dy upon L A capital Y. As I already told you, capital Y is Young's modulus. It's a constant. It's not variable. Mind it. Small y is a variable. So integrating both sides. Integrating both sides. So delta L will be integration d delta L is equal to, now M is constant, G is constant, L a constant, Y constant. What is left? Y dy. And limit is from 0 to L. So delta L comes out to be भाइयों बहनों mg upon L a y dy integration will be y square upon 2. Y square upon 2 and limit is from 0 to L. So delta L is equal to mg upon LAY. 2 can also be taken here and that is L square minus 0 square. Okay. Okay. So delta L comes out to be mgl upon 2ay. This is the answer. This is the answer. Okay. Please note everyone.
Excuse me, sir.
Yes.
Sir, could you please explain the graph part?
Noted everyone.
Yes, sir.
Understood also everyone. All right. So that is enough for today. We'll be studying further in next class. Tomorrow we'll be finishing this chapter. This is almost done now. Okay. Okay.
Okay, sir. Thank you so much, sir.
Okay.